Hey everybody, this is your chapter 4 overview. Let me go ahead and share the screen here. There we go. And here. All right, chapter 4, radio frequencies. Okay, kind of a long chapter. Okay, radio frequency fundamentals, understanding radio frequencies. Okay, we think about radios, we think about waves that kind of radiate out. Okay, a wide range of communications that we have, from actually radio, we listen to music, whatever, television, broadcast over radio, cordless phones. Don't have many of those anymore. They're still out there, but they're just rarely used as much. They were very popular back in the day. Wireless networks, obviously, and satellite communications. Okay, so it kind of radiates out depending upon the types of needs. I have a friend of mine and stuff. He's comes from a pretty well-off family, and he likes to go camping and hiking up in the mountains here in the Sierras. And his wife said, "You're too valuable to get lost." Okay, fine. Then you must take a satellite phone with you wherever you go, because we're not going to rely upon cellular in case we have to recover you, okay, or you get stranded. So he takes a satellite phone, just like you see in the movies, just to go camping, because he goes up to some pretty high places that are isolated. Anyway, happens out there. So radio communications, radio frequencies consist of alternating currents. Okay, is a basic idea of what is a radio frequency to communicate. Again, traditional and stuff, we're over a frequency over a copper cable and connected to an antenna, and we would then transmit those things out. Okay, understanding frequency antennas transforms these radios and then tries to propagate it. We have a transmitter, and then we have a receiver, right? One that sends the signal, one that receives the signal. Okay, there is what we call the sine wave, or the electrical current of a volt over a period of time. We have frequency transmission, successful communications. There are two components. Again, I talked about this a moment ago. There is the transmitter and then the receiver, okay, and there must be at least one on the other end. Now we get into characteristics of the wavelength, okay, how long the wavelength is. We can talk about the frequency of that wave, okay. We talk about the amplitude, the height of that wave, okay, and then shifting a phase, a wave that's kind of like row, row, row your boat, and the next person starts singing eventually row, row, row your boat, and then it's just, that's a similar song that has a phase shift, and so therefore goes, shifting from itself by, whatever angle degree that they're using, okay. And then we get into the frequency bands, and then a lot of the information about radio frequencies and ranges, okay, that you go through in your book, and coverages set by IEEE, okay, the number of devices and stuff that you can have, the size of an area, how much space do you need for a particular access point, the size of the area, the use, what kind of obstacles and stuff. If these are offices, building some days and stuff, we think of the old days and stuff, they're built out of wood, but there's a lot of aluminum and stuff, or metal, 2x4s that are in the buildings now. And so there can be all sorts of interferences that go in that process that can actually affect the signal quality, okay? And then again, hardware and output capacities. Okay, so we need to look at those capacities and throughputs and stuff, and then figure out how that bandwidth is actually going to accomplish its task. Now, in the radio frequencies and stuff that we get in the 2.4 gigahertz range, we typically have various channels. And again, you think about the old days, it's like, hey, let's turn into channel 3, okay? And so here's an example of a series of channels that are using channel 1 to cover an entire square foot area. Okay, we get into range and speed, okay, the visual line of sight, okay, any kind of environmental things or interferences that could affect this building. So like here, talking with here, if we obviously unobstructed, if we have trees or something like that, that might grow and start to interfere with this communication between the buildings, okay? So we're always trying to put everything on the highest rank, okay? Or we're using like a satellite, so we go communicate up and then back down again. Just depends, okay? Again, a lot of it has to do with cost and stuff, efficiency of what's going through, okay? And then what kind of things can cause interference in these various bandwidths? Well, sometimes we have overlapping signals, and we've heard that, with telephone calls, not as much anymore and stuff, but you start hearing, it's like, is somebody there they're hearing? Because there's been an overlap in the signal, okay? And some people are getting what sounds like two different channels at the same time because they have that overlap. Okay, so when you look at that process, it's kind of important. And then we have the various breakdowns of reflection and refraction and diffraction and so on. So I think what I'd like to do is to come back up here and show you a couple of short videos and stuff that deal with what is the radio frequency spectrum. Okay, now this guy has a bit of thick accent, so bear with him and stuff, but it's only about 5 minutes long. And then we'll go into another video, and I won't go through all of it. I will put those in Canvas. You can watch the full videos again as many times as you want, okay? But they'll go through the basic elements of signal loss or interference, okay? All right, so here's this first one. What is radio frequency spectrum?
So in this video, we are going to discuss radio frequency spectrum, which is a part of electromagnetic spectrum, starting from 3 kilohertz and ending at 300 gigahertz. So all the wireless things which you see over here lies between 3 kilohertz and ending at 300 gigahertz. So this spectrum is divided into further bands, starting from very low frequency, which is VLF, then there is LF, MF, HF, and so on. So this is a radio frequency spectrum, and you can see almost all the things starting from submarines to radio stations, satellites, telephones, Wi-Fi lies between this spectrum. So we are going to discuss a little bit about this spectrum. So over here you can see all the different frequencies and their abbreviations and frequency and wavelength. So very low frequency is abbreviated by VLF, and its frequency is 3 kilohertz and ending at 30 kilohertz. And its wavelength is starting from 100 kilometers and ending at 10 kilometers. So this is VLF. Then there is LF, which is low frequency, starting from 30 kilohertz and ending at 300 kilohertz. And its wavelength is starting from 10 kilometers and ending at 1 kilometer. So for those who don't know about wavelength, let's just discuss the wavelength as well. So what is wavelength? Wavelength is a distance between two peaks or two troughs, right? So over here you can see this peak is starting from here, over here from the red line, and ending at this peak over here. So starting from here and going down and again coming at the top peak is a one wavelength. Similarly, if we see from the troughs, it starts from this trough and ends over this trough. So this is a one wavelength. So this is a wavelength. And over here you can see when the frequency is increasing, like in MF, it's 300 kilohertz and ending at 30 megahertz, the wavelength is decreasing. In low frequency, the wavelength is high, or the long wavelength. Over here you can see, I should say, it's a long wavelength from 100 kilometers to 10 kilometers is a long wavelength. And if we go at the down where the frequency is increasing, like very high frequency and ultra high frequency, the wavelength is getting smaller and smaller, right? So this is one point which I want to clarify. And let's just
okay, we'll stop there. Again, I wanted to give you some of the basics. That first one here on that first screen I thought was really helpful because it gives us a visual idea, you know, of the various bands and frequencies. And again, think of those as being radio channels that helps your brain, or what we used to think here in the local area, we would talk about UHF frequency on our television. But, you know, I lived in Sacramento and a lot of those channels up north were under VHF frequencies, or, you know, vice versa, or it depends upon where the overlaps are. But those were our TV channels and stuff in those areas. But now when you start sitting there saying, okay, where do we live here for our computer networks, our satellite networks, you know, whereas basic radio frequencies, we dial in and we say, hey, we're listening to, you know, a 98.1, you know, radio station or something like that. Okay. Anyway, all right. So let's kind of end that guy here for a second here, and we'll go from that. And then let's take a look at this other one here that I wanted you to kind of watch here. And this has to do with the basics of radio frequency. Again, I'll let part of this one here, and both of these videos, this one's a little bit longer, but I won't play through the whole thing, but we'll talk about some of the basics.
Okay, so let's talk about our agenda for today and what we'll be talking about. First of all, we're going to be looking at our basics. So before we get into the 5 RF fundamentals, I do want to review some basics with you to make sure you have the terminology down. Then we'll get into the 5 RF fundamentals, which are channels, behaviors, measurements, interference, and analysis. And we'll look at those one by one. Our webinar will run until about 1:30 Eastern Standard Time. And so we try to keep them to about a half hour to not take too much time out of your day and yet provide you this valuable technical information. So first of all, RF basics. What we need to understand is frequencies, waves, and radios. The frequencies are the specific locations within the RF spectrum that we actually use to transmit our data or to pass signals on. The waves, of course, are the actual medium that we manipulate in order to modulate data and therefore transmit data. And then the radios do the transmission. So let's talk about this a little bit more. First of all, when we look at frequencies, the 2 primary frequency bands that we use for 802.11 wireless networks are the 2.4 gigahertz frequency band and the 5 gigahertz frequency band. Now, 2.4 gigahertz many years ago kind of won a battle because of being first to market. That is, with the original 802.11 standard that came out in 1997, sometimes called 802.11 prime, did not specify any operations in 5 gigahertz. It only specified operations in 2.4 gigahertz. And since that was first, these were the devices that existed. We then had a rolling effect that has stuck with us to this very day. And that is that because 2.4 gigahertz client devices already existed, even when APs came out that could support both 2.4 and 5 gigahertz, we still kept supporting 2.4 gigahertz because 2.4 gigahertz clients existed. And so therefore, we still find ourselves in that space today, which is not a good space to be in. 2.4 gigahertz is very cluttered. Some have said in recent months that 2.4 gigahertz is dead. This is, of course, completely untrue. How can you say that something that is alive and utilized more than anything else is dead? It's not dead, but it's certainly crippled. It's crippled because of the fact that so many devices operate there, not just our wireless networking devices, but many other devices as well. So 2.4 gigahertz is not an effective band for enterprise wireless LANs when we have control over the client devices that are going to be used. If we
now that may be true and stuff, but you know, when I think about a home environment, I think my 2.4 is probably okay. And it really depends. But when possible and stuff, I usually try to jump on the 5 gigahertz. Now, something he hasn't mentioned yet here either is the 2.4 is a stronger is a signal that can permeate walls a little bit better and go for longer distances. Here, that the diagram says farther versus the 5 gigahertz. So the 5 gigahertz is a faster speed communications, but it's a shorter distance. Okay, so there's other considerations and stuff that he's going through. All right, let's keep going a little bit further.
We can dictate that 5 gigahertz clients will be used. Then we want to use 5 gigahertz clients. Why? Well, we'll see later. There are many more channels in 5 gigahertz because we have much more frequency space. So the first thing to realize is that the frequencies matter. And the frequency is really just how often RF wave cycles per second. So how many waves per second are we creating? 20 hertz would be 20 cycles, 900 megahertz would be 900 million cycles, 2.4 gigahertz is 2.4 billion cycles per second. So higher frequency waves have shorter wavelengths and lower frequency waves have longer wavelengths. Now, the other factor is the wave itself. So the wavelength is an entire 360-degree movement of an RF wave. This is 1 hertz. And waves have characteristics that are important, like the amplitude of the wave. This is the strength or power of the wave. How strong is it? And the strength or power of the wave attenuates or weakens as it travels through free space and as it passes through materials like walls and doors and floors. The period is the distance between 2 identical points on an RF wave, and a phase is really not a feature of a wave, but it is the characteristic when 2 waves are compared with one another. That is, 2 waves can be in phase or they can be some degree out of phase. When 2 waves are in phase, if they are the same wave, they strengthen the signal received. When 2 waves are 180 degrees out of phase, they can completely cancel the signals, but certainly out of phase waves arriving at a receiver cause a weakening of the signal. Now,
So I had talked to you and I showed you a slide a little bit earlier and stuff on a 90-degree phase shift. And I made the example of about row, row, row your boat and stuff. So again, here's an example of 180-degree out of phase, okay?
How can you have multiple phases of the same signal? Well, you do that because of the RF behaviors we'll talk about later. The reflection that causes the signal to move around within a space so that you get multiple copies of the signal at the receiver at slightly different times, which means they're slightly out of phase or possibly completely out of phase. This is an important thing to consider, and it's one thing that we actually take advantage of in our modern wireless LANs with 802.11n and 802.11ac using what is called MIMO, multiple input, multiple output. We're actually taking advantage of these phase variations and using it to transmit multiple spatial streams. Now, the last thing I mentioned for RF basics is the radios. So the radios are the transmitters and receivers of RF signals. The antenna is not actually the transmitter. The antenna is the radiator. The antenna simply allows the electromagnetic waves to go out of it into free space and propagate, but it's not the actual transmitter. The transmitter, you could say, is the entire radio chain, the combination of the radio, any cables or connectors, the antenna, all of it together become a transmitter. It's also called an intentional radiator. Now, many devices have multiple radio chains. So when you see 3 by 3 by 3, that means there are 3 radio chains and we can send out 3 spatial streams. And this is an important thing to consider when you're implementing modern wireless LANs. So now let's begin talking about the 5 RF fundamentals, or the 5 fundamentals of RF that you have to know for wireless LAN success. The first one is channels. And we have different channels depending on whether we're in 2.4 gigahertz or 5 gigahertz. And we're about to see why I said that 5 gigahertz is so much better for implementing wireless LANs. In 2.4 gigahertz, you have a total of 14 channels. However, these 14 channels are spaced only 5 megahertz apart based on their center frequency. So you'll notice in the screen that channel 1 centers on 2.412 gigahertz. And channel 2 centers on 2.417 gigahertz. So notice they're only 5 megahertz apart. However, the channels are 20 megahertz wide for OFDM, which would be 802.11b, or rather, I'm sorry, 802.11g, and 802.11a in 5 gigahertz, but we're focused on 2.4 gigahertz here, and also 802.11n. So 802.11n and 802.11g use OFDM, and they use 20 megahertz channels. 802.11b and the original 802.11 use 22 megahertz channels. So the point is that because the channels are 20 or 22 megahertz wide, when we actually transmit, and they're centered on a center frequency, and these numbered channels are only 5 megahertz apart, that tells you that using channel 1, the actual signal itself is going to span channels 1, 2, and 3. And then the side bands, the extra energy that is just radiated as we generate a signal, is going to go even up to 4 and possibly 5, depending on the output power. This is why we say in 2.4 gigahertz, when you only have 11 channels, which is all we have in the US and in many other regions of the world, you only have 3 real channels that you can use. Even though there are 11, we can only use 3 of them, channel 1, channel 6, and channel 11. This is why hopefully in your enterprise wireless LAN on 2.4 gigahertz, when you do a scan of the environment, you see a lot of APs on channels 1, channel 6, and channel 11. Hopefully you don't see any APs on channels 2, 3, 4, 5, 7, 8, 9, and 10. Sadly, in mixed environments, particularly in shared spaces like office spaces and things like that, where multiple companies are represented, you see nearly all of these channels utilized. And this causes a lot of what we call adjacent channel interference. The channels are stepping on each other because their signals invade the other channel bandwidth. So 2.4 gigahertz, here's why it is so cluttered. We really only have 3 channels, and then add on to that all of the many, many, many devices that are actually there operating in 2.4 gigahertz. Now, when we get to 5 gigahertz, things are much improved. In 5 gigahertz, we have 20 megahertz OFDM channels. We have other channel widths as well. So you can bond to 20 megahertz channels for a 40 megahertz 802.11n or AC channel. You can also have 80 megahertz 802.11 AC channels and 160 megahertz 802.11 AC channels. Now, I don't recommend using 160 megahertz channels, even if they're available and when they're available, in any enterprise deployment ever. 80 megahertz channels are still up for debate in some enterprise deployments based on the fact that it has some dynamic channel capabilities.
Okay, I'm going to jump over to
Now,
behaviors.
the next thing that is one of the 5 fundamentals of RF you must know is RF.
These behaviors and stuff, which are also explained in your chapter and stuff, gives you, again, some good visual representation. So let's hear some more.
Behavior. RF, as it moves through a space, has a particular behavior set. And these behavior sets include scattering, diffraction, reflection, refraction, and absorption. Now, we don't have to get too fancy into all the technicalities of it today. You just need to understand these basics. And the most important ones we see indoors are reflection and absorption, with some refraction and diffraction as well, but mostly reflection and absorption is what we think about. So reflection is the RF signal reflecting or bouncing off of some kind of reflective material that has a size greater than the wavelength. And so we're talking here about metal objects like filing cabinets, things like that. These can all cause reflection, and many other objects cause some level of reflection. Its reflectivity factor may be higher or lower, but some level of reflection occurs. Absorption is when, technically speaking, the RF energy is converted to heat. And so what happens is the RF energy converts to heat as it is absorbed, and therefore it is lost. This is why your microwave oven works, okay? You close the door, you start it up, and all of a sudden 2.4 gigahertz radio waves are blasted into the microwave oven. These radio waves are absorbed very well by water, and so the absorption is the converting of the electromagnetic waves into heat. And the end result is that your liquid heats up, or anything that has moisture in it that's in the microwave. Think about it like this. Have you ever noticed that you can take a glass of water, sit it outside, and if the light waves pass through the glass, it will actually heat up the water more than just contacting water directly? Well, this is in part because of absorption and refraction behaviors. Now, refraction is where the RF wave bends as it moves through a material. So it's going to change slightly. And the example I like to use with this is take a clear glass, put some water in it, and take a butter knife, place it in the glass and look at it from the side. It will appear to you that the knife breaks in two at the point of the water. And so you'll see the part of the knife that is in the water appears to be in a different location than where it really entered the water. There's this kind of illusion that occurs. That's because the light waves are refracting as they pass through the water. And so refraction can also occur, slightly changing the path of an RF wave, and of course, some absorption as well. Diffraction is how an RF wave may move around a large object and sometimes change direction. And then scattering is when an RF wave hits something a little different than reflection that is smaller than the wave and breaks it up and sends it in multiple directions. It's really many, many reflections of the RF wave. So why are these behaviors important? Well, they're the reason that when you put an AP in a room in a building, those radio frequency waves can get to nearly every place in the room and also other rooms, because they're reflecting around as they move throughout the space. And of course, they're passing through some materials as well. Now, the interesting thing is that this can be bad for old type of networks like 11BG and 11A, but it can be very good for new networks like 11N and 11AC, because these multiple signals give us this reflectivity that allows us to have multiple spatial streams, separation of data based on phases and other factors. So RF behaviors, key to understand. The next of the 5 fundamentals of RF you must know, the third, is RF measurements. So we need to know how we look.
So this next part goes to the measurement. It's very geeky and technical and stuff, so that's fine. And then this video ends with the section on interference as well.
The constellation
Again,
chart.
let me pause. Information as well. So I'll put this full video and stuff in the Canvas website, but I think this gives you kind of a good understanding of what Chapter 4 is about. Let me go ahead and stop sharing. All right, and I'll end this recording so you have a good one, and we'll see you in the next video.